In today's lesson, we're going to introduce one of the most important concepts that we'll talk about this term, which is the idea of a confidence interval. So confidence intervals are central to the idea of quantifying uncertainty within statistics. And so we're going to talk about how that works in this lesson. And then in the coming lessons, we're going to see specific examples of how we might find confidence intervals in different situations. So there's quite a few objectives for the lesson today. First, we want to understand the need for and the utility of confidence intervals. Right? We're going to try to understand what the general process for constructing a confidence interval is, and then we're going to see how we can construct confidence intervals for normal population means. We want to spend quite a bit of time talking about the correct interpretation for a confidence interval. That's one of the most important things to do from confidence intervals. And then finally, we want to try and use what's known as the margin of error to calculate necessary sample sizes based on this idea of confidence intervals. Right? So there's quite a lot that we'll try to cover today. Hopefully we can get through it all and that everything here is very clear. So I'll start with just sort of a point, which is that from the start of the course, I've been talking about how statistics is about quantifying uncertainty. And now that we're at confidence intervals in the course, we're ready to finally start doing that. Everything that we've been doing up till now has been, related to different aspects of this quantifying uncertainty, but confidence intervals sort of marks the first point where we're taking everything that we've done until now and actually trying to explicitly quantify how much uncertainty is there in the estimate of something. So, why do we need confidence intervals? What are confidence intervals? Why is this such an important topic? When we have a point estimate, that's giving us no information about how reliable our estimate is, right? That's just a single value. And as we were talking about, we know that that single value is probably not going to be correct. But what we don't know is how close is it to being correct, right? We don't get sort of any sense of how certain or uncertain are we about that estimate. We know as a general rule that theta hat won't equal theta exactly, but we also don't normally care about it being exactly perfect, right? There's very few situations where you need to get exactly the right estimate out. And so are we going to be close? That's sort of the idea that we're trying to address. In some sense, if we came up with a range of plausible values for theta, that would work out better, right? If we said that we're pretty sure that theta falls between, A and B, then that can sort of let us make decisions about, what happens if theta is actually A, what happens if theta is actually B, and what happens if it's somewhere between those two extremes, right? And so, in some sense, having this interval of possible estimates for the value of theta is preferable. It allows us to know how certain or uncertain are we about the decisions we're going to be making. The more narrow that range of possible values is, the more precise we have, right? So if A and B in some range that we're giving are very close to one another, then we're quite certain of what that estimate is. But if A and B are really far apart, then, we're a lot less precise, where we have a lot less certainty about this. And so all of this brings us to defining confidence intervals. And a confidence interval is going to be one form of interval estimate, which give a range of plausible values for a parameter of interest. Okay, so instead of working from a single estimate, the confidence intervals give us a whole interval of them. We call confidence intervals random intervals, as they are intervals that have random endpoints. So we have some starting point of the interval, some ending point of the interval. Both of those are going to be estimated from random data. And because of that, these are going to be random intervals. We're not going to know exactly how long our interval is going to be. That's going to depend on the data that we actually observe. But we're going to look at procedures for creating these upper and lower bounds. So how do we go about constructing a confidence interval? And I'm going to go through this process very generally to start. And the idea with going through this generally is that over the next few lectures, we're going to see specific ways of computing confidence intervals. But I want to make the point that this process here applies no matter what we're looking at, right? I think there's this tendency in intro stats courses to teach a bunch of different types of confidence intervals as though you need to memorize those specific types of confidence intervals. And while I think after you've worked with them for quite some time, they do sort of become ingrained in your brain, the idea with confidence intervals is far broader than that. And the process itself, I think, is actually sort of intuitively pleasing once you are able to wrap your mind around it. And because of that, if you can understand how to generally construct a confidence interval, you never really need to memorize anything, because you can just sort of think about the general procedure. What are we actually doing under the hood? And then use that in any of the specific situations that come up. So don't worry too much if the general process here is not clicking right away. We'll have plenty of times to see this in action over this lesson and the coming lessons. But I would invite you to revisit this general procedure before you try to go off and memorize all of the different types of confidence intervals we might have. So to start, let's suppose that we have some point estimator, which we'll say is theta hat, and we're trying to estimate theta. Okay, we've discussed that theta hat comes from some distribution, and I'm just going to say that that distribution is, say, omega of theta, right? And so what do I mean by that? Well, omega of theta could, for instance, just be a normal distribution with some mean and sigma squared, right? And then in this case, theta is going to be the mean and variance, right? We could also think about it being, say, an exponential distribution, right? We saw those with lambda, and then in that case, theta is going to be lambda, right? So we're just using this to remain as general as we can. Now, theta hat can be thought of as a random variable from this distribution, right? So we can write that theta hat follows this omega of theta distribution. And that's because theta hat is an estimator, not an estimate, right? So this is why it's sort of important to have that distinction between estimators and estimates confident in your mind. And so because it's random, we can make probability statements about theta hat, right? And in particular, if we knew what the distribution was, then we could find two values, right? The probability that A is less than or equal to theta hat, which is less than or equal to B. And we could say that this probability is going to equal some value, say 1 minus alpha, right? And so depending on what omega is, depending on the underlying distribution, A and B are going to change, right? And also depending on what we select alpha to be, it's going to change. But we know that generally speaking, we know how to compute this kind of probability statement here, right? If we were to given the distribution. And in particular, what we're going to see is that generally A and B are both going to depend on the distribution and the parameters, right? So these are going to be functions of theta. And so if you knew the distribution, then you could compute this probability statement here, and you could find these endpoints that are going to be functions of theta. Now, often what we're going to do is select alpha to be some small value, say a value of about 0.05 is pretty typical. And the idea is that these endpoints, if we could actually find them, if we knew what they were, are going to be the endpoints that we're 95% confident, if alpha is 0.05, that the estimator is going to end up falling between, right? So the estimator has a 95% chance of falling between A and B in this case. As we mentioned, these values of A and B are both going to depend on the distribution and in particular on the true value of theta. And so as a result, we can think about A, say, as being some function of theta, right? So we can say A of theta. And if we have this expression A of theta equals theta hat, then what we could do is actually form some theta based on the inverse of A, right? If we could just solve back for this inequality as it relates to theta hat, then we'd have an inequality where we have, that should be an inverse. Then we'd have this inequality where we have theta over on the right side, or on the left side here, and then theta hat on the right side, right? So this is just going to be theta, and we don't know which direction this inequality is going to go, but it's going to be some function of theta hat. Okay, and so we could do the same thing with b as well. So we can solve these two endpoints of this equation. And what that's going to give us is on the one side of this equation here, something that we can compute, and theta is going to be on the other side of the equation. This is the process for forming a confidence interval around theta, right? So the idea is that we start by making a probability statement about our estimator, and then we invert that so that it can be a statement about the parameters that we don't know anything about. Okay? Once we've solved for these two values, we'll typically have upper and lower bounds on theta. And exactly what those upper and lower bounds are going to be is going to depend on what those functions look like, right? Sometimes the a will give us the lower bound, sometimes it'll give us the upper bound. That's not super important. What's important is that by solving these two different sets of equations here, we're going to get upper and lower bounds on theta. These are going to often depend on other unknown parameters, right? So if we're trying to form a confidence interval for the mean, this might depend on the variance. And if that's the case, then we're going to want to plug in some estimates for those. If that's the case, if they come up, we can plug in our estimates, we can use other strategies, right? So just noting that sometimes even once we have this, it's not going to be a fully computable example or a fully computable function. That'll be all right. There's typically ways of working around that, but this is still the process that we're going to try to follow. We take the lower of the two bounds to be the lower bound, and we take the upper bound and then call the interval, and I have this written backwards on the slides. I'll correct that by the time it's uploaded. We would take the lower upper to be the confidence interval, right? And so all of this starts with that statement about the estimator. We invert those two bounds. One of them is going to be a lower bound, one of them is going to be an upper bound, and we take that and we call that the alpha level confidence interval for the parameter of interest. Normally, we're going to pick alpha to be, say, 1% or 5% or 10%, and the idea is that alpha is somehow measuring how confident we are in this interval. Okay? So let's take a concrete example here. Let's make sure that all of this is making some sense. And so I'll actually pull open the whiteboard and work through what's on these slides as we go. So let's suppose that we're working with a normal population and we have some unknown mean, but we have a known variance. We're sigma squared. Okay, so we know what sigma squared is. Okay, and then we're going to end up using the sample mean. So x bar is the theta hat. Okay. Now, what we saw when we talked about our sampling distributions was that x bar, when it's a normal population, is going to be distributed as a normal distribution with mean mu, and the variance is going to be sigma squared divided by n, right? And if we think back to how we dealt with normal populations, generally speaking, well, oftentimes what we would do is we'd say, instead of dealing with a normal that has arbitrary mean and variance, let's sort of centralize this, right? So we take x bar minus mu, divide that by the standard deviation here is going to be sigma divided by the square root of n. And we can say that that is going to be normal 0, 1, right? And so if we now say wanted to take alpha to be equal to 0.05, then we need some critical values from the normal distribution. And in particular, we want some values a and b, so that the probability that a is less than or equal to z, which is less than or equal to b, is going to equal 0.95, right? And so you could think about this as taking the CDF at b minus the CDF at a. This is we want this to be 0.95, and it makes some sense to think about doing as much above and as much below, so we're taking these to be symmetric, and basically what you can do is you can solve for b is going to have to be approximately 1.96. A is going to have to be approximately 1.96, right? These are the critical values from the normal distribution. We've seen how to compute these when we were looking at probabilities, generally speaking. Right, so now what are we saying? Well, we're saying that the probability that we have negative 1.96 less than or equal to, in this case, it's going to be x bar minus mu over sigma squared, sorry, should not have the square there, sigma over square root of n, less than or equal to 1.96 is going to equal 0.95. Okay, so we have sort of those endpoints computed. Now what we can do is invert these two bounds here, right? So we have negative 1.96 less than or equal to x bar minus mu over sigma divided by the square root of n, right? And we are assuming that x bar is known, sigma is known, root n is all known, right? So we want this to be an interval or a bound for mu here. So we can bring over just about everything to the other side here. And so you're going to get 1.96 times by the denominator here. And then if we subtract off x bar, it's going to be less than or equal to negative mu, multiplied by negative 1, and we get 1.96 sigma over root n plus x bar has to be greater than or equal to mu. And if we do the exact same thing from the side of x bar minus mu over sigma square root of n has to be less than or equal to positive 1.96. What we're going to find is that this is going to equal, when we actually solve through this, we'll get x bar minus 1.96 sigma over square root of n. And so, of course, this is going to end up being, and this will have to be our lower bound, right? It's going to have to be less than or equal to mu. And so all of this comes together, and we say that the confidence interval is going to have to equal x bar minus 1.96 sigma over square root of n, x bar plus 1.96 sigma over the square root of n. We could have chosen a different value for the 1.96 if we didn't want alpha equals 0.5. But this is going to be our general process here, right? Where let's review what we did. We started with this assumption of things being normally distributed, where we knew the variance. We wrote down a probability statement that we actually knew the endpoints on, and then we take these expression about our estimator and we invert it in order to be able to make conclusions about the endpoints for our confidence interval. So these notes here are just going to summarize that procedure that we just walked through. So if we take, say, alpha equals 0.05, then we want the endpoints such that it's going to be 0.95. Instead of using 1.96, we could have used the empirical rule, right? This is one of those candidates where it's useful. But as we noted, it's generally going to be easier to standardize this, right? So we take z to be x bar minus mu divided by the standard error there. Then we can use our critical values. Using those critical values, there's no dependence on outside parameters. So we had noted that you might have endpoints that depend on parameters that you don't know. In this case, that's not going to be the case, but it could come up where that's the case. And so then we get this expression where taking those two critical values, we have the probability equals 0.95. And so we can solve for the upper and lower bounds. The lower bound is going to be x minus 1.96. Upper bound is going to be x bar plus 1.96 times the standard error. And we'll often write that interval as x bar plus or minus 1.96 times sigma over the square root of n. So this process right here, like I said, follows a general procedure. We're going to see this implemented in other populations. But again, anytime that you can make this probability statement about your estimator, you can then invert those endpoints, and that's going to give you the confidence interval that you care about. So before data collection had begun, the process that we defined had a 1 minus alpha chance of constructing an interval which contained the truth, right? And so What do we mean by that? Well, we took an interval that we knew there was going to be a 1 minus alpha chance of the estimator falling in, and we inverted that to say something about the true parameter values. So because of that, before any data has been collected, there's going to be this 1 minus alpha chance of constructing an interval that contains the truth. Now, this statement is incredibly important, so I'm going to emphasize this. It's bolded in the slides. It is not correct to say that the probability that theta is in this interval is 1 minus alpha. In fact, it's never correct to say this. The reason that we can't say this is because theta is some fixed value. Theta is not random. Theta hat is random, but theta is not random. And so once you've formed a confidence interval, you can't say that you're 95% certain that the true value is in that interval. Okay? Once the interval has been constructed, the truth is either in there or it is not in there. The probability that theta is in that interval is either 1 if it actually contains it, or it's 0 if it doesn't. And so how do we correctly interpret this? And the idea is that if you're going to repeat this procedure many times, in approximately 1 minus alpha percentages of the cases, the constructed interval is expected to contain the true value. Right? So we have to go back to this frequentist interpretation of what probability is. On any given time, you can't make a probability statement about it. However, if you're going to be using these confidence intervals and constructing them sort of many different experiments, then in, say, 95% of your experiments, you're going to expect that the interval contains the truth. And so this is often sort of a confusing interpretation. So I want to sort of use a thought experiment here. And let's imagine that I have a bin, and in that bin, I have 95 red balls and 5 blue balls, right? And I'm going to reach in and I'm going to draw a ball without looking at it. And before I've looked at it, before this has actually happened, there's a 95% chance that that ball that's going to be in my hand is going to be red, right? 95 out of 100. However, once I have that ball in my hand, there's no longer the same probability statement. If I take a peek at what's here, I can't say, well, now there's a 95% chance that this ball is red. This ball is either red or it's blue, right? Once we're looking at it, we know, is this red? Is this blue? But before we've looked at it, the procedure that we're using is going to give us this 95% chance. We know that if we're going to do this a bunch of times in a row, that 95% of those cases are going to end up with a red ball in my hand. But as soon as we're looking at what ball's in my hand, it's either red or it's not, right? There's either a 100% chance that this is red, or there's a 0% chance that this is red. The same thing is happening with confidence intervals. So to reiterate, if you see a confidence interval, the correct way to interpret it is to say, if you were to follow this procedure in exactly this setting many times, in approximately 95% of those cases, you would expect that the true value is contained in the interval that is constructed. If you're given one interval, you can say that you're 95% confident in this, but what that means is that you're 95% confident, or you would say that in 95% of these intervals, if you were to do this a bunch of times, the true value would be there. You're never saying there's a 95% chance that this interval that I have contains the truth. Okay. And so it's sort of there's a slight nuance. I hope that the example about drawing a ball from the bag helps. But I would just say the main thing here is to practice writing down your interpretations for what confidence intervals mean. And the point that I would make is if you're not talking about repeatedly doing an experiment, then the interpretation is probably not the correct one. So there's a few important cases or points that I'll make on confidence intervals. Oftentimes we noted that you'll use a 1% or a 5% or a 10% confidence interval, but the level is going to be determined based on the different use cases. And depending on your use case, different critical values are going to be required. And I'd sort of encourage you to think about what happens as you choose different values, right? So if you wanted to have an 80% confidence interval, how is that going to compare to a 99% confidence interval, right? Now, what if I asked you to form an 100% confidence interval? How would you go about doing that, right? What would that actually look like? And you can start to see, as you're increasing your confidence, well, you're going to require larger and larger intervals, right? You need to have a wider interval to be more and more confident about it. And so there's this trade-off between how confident are you in your estimation procedure and how useful is this interval going to be to you. And so because of that, what we really want to do is tailor the level that we're using to the specific situation that we're in. If we need to be very certain about it, because, it's sort of like a life or death estimate, then we want to increase the confidence in those estimates. If it's like kind of not that important, well, then maybe we can lower it a bunch and get a smaller interval. Right? And so that's going to be situationally dependent. In general, we're going to use plus or minus z of alpha over 2 for normal populations. We've seen these critical values from earlier in the course. We're normally going to use symmetric values when we can. When the distribution relies on unknown parameters, the interval is not going to be constructed exactly as we've just described, right? And that's where you're either going to have to estimate those parameters or use a slightly different procedure. Now, just as a point, if we find a statistic whose distribution does not depend on the unknown parameters, we call this a test statistic. So in that case of the normal population that we just saw, once you've standardized, that's going to be a statistic that does not have a distribution which depends on the true value or the unknown parameters, right? So because of that, we'd call it a test statistic. Test statistics are generally going to be quite useful for constructing confidence intervals. We're not going to focus too much on finding test statistics, but just as a point, if you're given a test statistic, it becomes a lot easier to work with to find a confidence interval. We're going to consider confidence intervals mostly that are symmetric around our point estimate. They don't have to be, right? You could have shifted it so that it's not symmetric, but generally we're going to want them to be symmetric around the point estimate. Now, the final topic to consider with relation to confidence intervals is the idea of margin of error, right? So if we have a symmetric confidence interval, then we know that the distance from the upper bound to theta hat, or from theta hat to the lower bound, is going to be equal. That's what we mean when we're saying it's a symmetric interval. And we call that distance, the distance from our point estimate to one of the endpoints, the margin of error. The margin of error is half the width of the confidence interval. And the basic idea is that we're saying that this is our point estimate plus or minus our margin of error, right? And so because of that, it's half the width if it's a symmetric interval. And so if we define the width to be w, the margin of error is w over 2. The margin of error gives us an estimate of how precise our point value is. And the smaller the margin of error, we'd prefer that if everything else is equal, right? So if we can have a very small margin of error, then we're fairly certain in that point estimate we have. If we have a very large margin of error, we're not so certain in that point estimate. And generally speaking, we're going to see that the margin of error is going to shrink as alpha shrinks and as the standard error of the estimator shrinks. So if we have a smaller standard error, then we're going to have a smaller margin of error. And if we have a smaller alpha, if we have a smaller alpha, we're going to increase the margin of error. But if we have a smaller confidence level, right? So this should not say the margin of error will shrink as alpha shrinks. It should say the margin of error will shrink as the confidence level shrinks, right? It's also typically going to depend on the sample size. Okay, so we saw in the case of the normal population, and let me pull open the board over here again. We saw that the confidence interval that we found in the case of a 95% confidence level was going to be x bar plus or minus 1.96 times sigma over the square root of n. Right? Now, this 1.96 was actually just the value of z for alpha over 2. Right? And so, in general then, the margin of error in this case is going to be z of alpha over 2, so the critical value, times by sigma divided by the square root of n. Right, so this is going to be our margin of error. And so we can see that as alpha is going to get smaller as we're pushing into the further and further into the tails, the z is going to increase. I guess I should point out that we're sort of thinking of taking the magnitude of this, right? As it's written here, z's going to be a negative number. That's fine. We don't actually care very much about that. So as alpha increases, the margin of error is going to decrease, right? Or vice versa. As the standard error, which is this piece here, right? This is the standard error of x bar. So as the standard error increases, the margin of error is also going to increase. But we can see in particular that if we were to hold everything else constant, so if z or sigma's constant and z's constant, and we increase our sample size, right? Well, then we're going to have the standard error get smaller. And as a result, the margin of error is going to get smaller. And so this makes some sense, right? The larger the larger the sample we're taking, the smaller our margin of error is going to be. And so let's say that we were in a situation and you're, say, doing manufacturing and you want to be able to estimate with a particular margin of error. You need to make sure that you're plus or minus some value from the truth, right? With some set confidence level. So the idea here is that we want to find an estimate, x bar, which is going to be plus or minus m with confidence level alpha. Okay? And so the question that we have is, how large n should we take in order to achieve this? And the nice part is that at least in this situation here, we can actually just do this calculation, right? Because what we're saying is we want m to equal z alpha over 2. We've defined what alpha is, so this is just some value. We're still assuming that sigma is known. Divide that by the square root of n, right? And so if we want the margin of error to be at most our value of m, then what we want to do is we want to say m greater than or equal to this value, right? We can bring over the square root of n, divide by m, so then we get the square root of n has to be greater than or equal to z of alpha over 2 times by sigma divided by m, right? And if we just square both sides here, then we get n has to be greater than or equal to z of alpha over 2, sigma over m, all of this squared, right? And so then we would want our sample size to be at least this large in order to achieve the set margin of error, right? And so this becomes a useful technique when we're trying to design experiments, right? You can set what you want your margin of error to be, you can set what you want your confidence level to be, and then you can say our sample has to be at least this large. So it's going to come up sort of again and again, and of course this example was specific to the normal population, but we're going to be able to do a similar thing with other populations as well. Now, if sigma is not known, which is going to be typical, it's going to typically require an estimate, but that's going to be okay, right? And so then the idea is, using these confidence intervals in a slightly different way, we can start to plan out the experiments that we're going to run. So again, that was a lot of information. I'll point out that over the next few lessons, we're going to be talking about specific forms of confidence intervals, so we're going to get a chance to revisit all of these concepts sort of over and over again. Confidence intervals are random intervals that quantify uncertainty in point estimation. They're formed by inverting the sampling distribution for the parameter of interest. They can be interpreted based on repetitions of an underlying experiment. Remember that we're thinking of the interpretation of a confidence interval is going to be, if you were to repeat this experiment over and over and over again, then in 95% of cases, the true parameter is contained in the interval. And the margin of error is a measure of the size of our confidence level, and it's useful to help us in sample sizing, right? So it's that plus or minus value, and we can sort of invert that procedure to calculate a sample size that's necessary. So again, I hope all of this was clear, and I hope that over the coming lessons that this will become more and more clear as we investigate the sort of specific procedures to different situations that we might care about. So I hope to see you all in those coming lessons.